Hey guys, welcome to the next tutorial of ethical hacking and pen testing with our own operating system Kali Linux. So in the previous tutorial, I taught you about the ICMP redirection, and just before I proceed, I'd like to give you I'll go through a short discussion of my previous Okay, so over here it would appear as if the ping program does not reevaluate the routing table during runtime. The reason for this is explained quite elegantly by Richard Stevens, as I told you previously, that this function only works for raw IP protocol, that is UDP and TCP. So this time our packets have taken their expected path and travel immediately through R2 rather than first traversing the default gateway R1. For every destination that host A receives a redirect, it will install a redirect host based route in its routing table. In this small example, it could potentially install up or set up to 255 routes and 32-bit mask. Just consider how many potential host-based routes this could generate for networks with more inclusive prefixes. For example, a single route with class B mask could potentially add up to 65,535 redirects. Certainly, it would be better for host A to be fitted with some better method of discovering what traffic to send through R2 instead of relying on ICMP redirects, because actually going ahead and redirecting 65,535 redirects, it sounds exhausting, and it is exhausting, because if you go ahead and try to do that, you may not even be able to get the redirect, stating that you will just be in a loop and you'll waiting like forever to go ahead and get the redirect. Thus, depending upon the OS implementation, these host based routes can have the characteristic of being short-lived. Solaris implements aggressive aging, where Solaris operating system it implements aggressive aging where redirects will only last for a specified amount of time. So let's say, for example, if I have redirected something to A and it does not respond for, let's say, around 10 seconds, 20 or 30, whatever the time may be, then the timer will expire and it will not be able to go ahead and send anything back. Each redirect is given a short lifetime value and will be automatically removed from the routing table when the timer expires. This is to ensure that redirects do not remain in the routing table indefinitely, at the risk of further going ahead and freezing other data as well. So in BSD networking code, redirects will be removed if they are being used by TCP, and only after the fourth consecutive retransmission attempt they will be removed. Router and gated perform similar forms of redirect expiration. Since ICMP redirects are dynamic and may not reflect the most current topology, it is nice to have an automated method of redirect expiration. Note that ICMP redirects can also cause problems in firewall environments where flow traffic patterns are non-deterministic. Just consider this following example. Figure 3 looks like, okay, just let me check. So over here, this figure looks quite similar to the previous diagrams, but suppose that host A's default gateway is not a firewall, that is, it is now a firewall instead of a router. If host A were to receive an ICMP redirect from its default gateway, probably only part of the traffic flow from host A to host B would be seen by the firewall. Asynchronous flows pose particular problems for stateful firewalls because they need to see the entire flow cycle. This is especially the case for TCP traffic, when individual packets can point to state transmission such as a beginning, such as SYN or SYN-ACK, or the middle such as the ACK PSH, or the end such as FIN ACK RST. If the firewall were only to see the beginning of the flow or part of it, it may take an extra long time to time out entries from the session table because it was not able to see the middle and the end of each flow, and again it may again go over and get disconnected. So the problem is exacerbated if an ICMP redirect only gets acknowledged by a host after the initial TCP handshake has completed. Firewalls rely on timeouts to age out old entries in cases where TCP control traffic is not available. Although embryonic TCP connection timeouts are generally an order of magnitude smaller than timeouts for established TCP connections, they can still lead to firewall session entry table converting into exhaustion. So a common design flow is that firewall security in this topology could be bypassed altogether if host A were to simply create a static route to host B instead of using its default gateway. This is probably not what the network architect intended when placing a firewall in front of the host A if she or he was looking to filter traffic properly from host A to host B. So in short, what I'm trying to say is that whenever some data has been sent out, the host A should know whether it should use the default gateway through a firewall or a blocked router, or it should know that it should go through the port 2, that is router 2, through which it should be able to connect to B. So the person needs to know, the data needs to know where it is actually going through. Finally, redirects could be used by an attacker that has some knowledge of the network topology to inject malicious routes into the host routing table. This could case a denial of service against the host or specific destination it is trying to reach. One example of such a program would be ICGen. I'll go ahead and talk about that at the later part of this tutorial. It is a utility developed by an author simply for research that is capable of sending any type of ICMP unreachable message. Older Microsoft variants are much more susceptible to this form of attack since less security precautions are out in place, and newer operating systems make this more difficult to spoof, but not altogether impossible though. But there is still a good news. Fortunately, there are effective tactics when dealing with networks that wish to send ICMP redirect, aside from disabling them altogether, because disabling them will not just go and help us, right? That's why. So generally these types of network can be re-architected through one of the following means. A. Changing the network configuration to remove the possibility of multiple non-redundant gateways for a host. B. Changing the network configuration to make the gateways redundant. C. Adding optimum static routes to the host for the networks in question. And the last and the foremost important, adding the capability for learning dynamic routes to a host. So, and the last and the foremost part would be, not the foremost, the ultimate thing that you would like to do in your environment would be to go ahead and make the host intelligent enough to understand whether it should go ahead and pass through a firewall or it should go through any other gateway through which it could go in and get access or give access to host B. And the firewall should be good enough to understand whether it should go ahead and force feed the data to go ahead and cancel itself if it's going to go through another gateway, or it should go ahead and allow it quickly just by going ahead and scanning it from the start to middle as well as the end, and knowing how to go ahead and redirect that. So though ICMP redirects serve to point out issues with suboptimal routing, network re-architecturing should be favored over their use. Well-designed networks should never lend themselves to the reliance on or desire for ICMP redirects for reasons of performance, consistency, reliability, and security. ICMP redirects are bad, that's why. So in short, that you should make your network so good that you should be able to know whether it should be able to, or in fact you should never be able to, you should not go ahead and disable ICMP redirection, I'm saying. But what I am trying to convey is that you should be able to know whether you should be able to go ahead and transfer data through different routes and through different gateways, and even if let's say for example, if the host A transfers some packets to, let's say let's assume that this firewall is a router. I'll just go ahead and go back to my previous one. So let's say for example, if the host A tries to send something to host to the router A, and as soon as it gets the redirect, it should go ahead and quickly pass it through router B rather than going ahead and searching default gateways. So there should be specific gateways set up already before anything goes further on, so that you know exactly what is happening, and it should know exactly from where it is going. And the final thing that I'd like to convey to you would be, avoid traffic jams, try quantum tunneling. It is the most famous quote of all time. I don't know who said it exactly, but this is very famous. So quantum tunneling, to be in technical terms, I can say as using SSH, secure layer. It is going ahead and using there's a most famous application which is used that is called as Putty, P-U-T-T-Y, and you can go ahead and download it from over here. Let me just show it out to you. So as you can see, this is a free SSH and Telnet client for Windows. And Ubuntu, Kali Linux, they have all inbuilt SSH clients, so you don't need to worry about that. For Windows, you can go ahead and use this, and this is a very, or I can say extremely secure Telnet client used by most of the people out there. You can go ahead and connect to any Windows you want through the SSH tunnel, and you won't even face any kind of traffic jams because it's quite or extremely fast, and you can run multiple computers, whereas using graphic user interface can go ahead and run only one computer. Yes, so that is it for this tutorial, guys. In the next tutorial, I will actually be going ahead and showing you some actual examples of going ahead and killing your network, or using some tactics to go ahead and defend your own network, as well as using your exploits and injecting them into softwares. And at that point of time, we will be using ItterCap, which is again used for man-in-the-middle attacks.